Like I went on the grind the other day and I pulled in
Okay.
really bad entrance.
So again, recapping what we've covered so that we know exactly what is on the quiz tomorrow. So in 9.1, the very first thing that we talked about was sequences. Remember that sequences is just a set of numbers, right? They are the terms of a sequence are generated using some term generator. We can talk about whether that series converges or diverges by doing a we're talking sequences here. Just do a limit, right? Just do a limit as n goes toward infinity, okay? Just do a limit as n goes toward infinity. If you get a value, then the sequence converges to that value. If you don't get one, then the sequence diverges, meaning that term generator is not allowing you to approach a single value, okay? So that's a sequence. Series, when we add together the terms in a sequence, okay? And we said that we're interested in whether or not those series converge or diverge. So this idea of a sequence converging allows us to do something called the nth term test, right? We do the limit as n goes toward infinity for that term generator. If we get some value other than 0, right, that means that the sequence is converging to some number. And a series says that we're going to continually add those terms together. So if you do the nth term test, which is where you're doing the limit as n goes to infinity for the series, and you get a value other than 0, then we say that the series does what? Diverges, okay? Then we came across geometric series. We said those are normally the easiest ones to recognize. A geometric series is a series where we take a value and we multiply by a common ratio over and over again, right? If the absolute value of that common ratio is less than 1, what do we say about the geometric series? That it will converge, right? And that's because you're multiplying by a number that's making the next number smaller and smaller and smaller and smaller until it approaches 0. So we actually have a formula that allows us to figure out the number to which a geometric series converges. And what's that formula? The first term divided by 1 minus r, right? And that'll tell us the number to which the geometric series converges. If the absolute value of the common ratio is greater than 1, then we say that the series does what? It diverges, okay? All right, so then we came across some other types of term generators that were not geometric, but when I did the nth term test, they gave me a value of 0. If you do the nth term test and you get a value of 0, the series may or may not converge. You have to do some more work there. So if it's not geometric, then the next thing you may want to look for is, does the series lend itself to the integral test, which was section 9.3. When we perform the integral test, we do the integral from 1 to infinity of the what? The term generator, right? And if the integral from 1 to infinity of the term generator converges, then we get to say what about the series? That it converges. And if the integral from 1 to infinity of that term generator diverges, then we get to say that the series also diverges, okay? And I'm going to show you, I'm going to clarify that once again, but I'm going to do it at the end because I want to make sure that we get through all of the notes, okay? We also said, we talked about this idea of a remainder or an error whenever we use the integral test. Remember that the integral test can be used, the actual integral, okay, we're going back to what Mary said a few days ago, which was in reality really good, okay? Third period kind of talked me out of her idea, but in retrospect and in looking at some things I've found online and in talking to some students, that idea is good, okay? And remember what Mary proposed that day was, when we are summing together an infinite series, aren't we just really integrating, okay? Yes and no, right? We are summing together an infinite number of y values, right? Whenever we find the exact area under the curve, we're adding all of those together. And remember, we're doing it with rectangles whose widths are approximating 0 when we find the exact value, okay? So what Mary did that one day was she graphed this on her calculator. It was a geometric series. We knew that it converged to 3, so I could say that the exact area from 1 to infinity of that function was 3, and that looks, that looks something like this when I find the exact area, okay? But then here's the other way. Here's the way to represent the series as an integral, okay? This is the actual integral where everything gets shaded in. The series can be represented as that integral like Mary suggested, but I wouldn't be coloring in, it wouldn't be solid coloring, right? Because with a series, we are only interested in the integer values, okay? So if I want to represent the series as an integral, it has to be with these rectangles of width 1, okay? And that's why Natalie was very opposed to Raphael's idea of stacking those values on top of one another. She was good with it. She's like, if you stack them as rectangles on top of one another, then I get it. So however that works for you or doesn't work for you, okay? But the idea is when you're summing together a series, you are really summing together the area of all of those rectangles, okay? And so what we find out is if it is drawn this way, okay? If your series is represented this way, where it's drawn underneath the curve, and the integral converges, then the series would also converge because those rectangles are underneath the curve, right? So if the solid area converges, it would make sense that just the area of those rectangles would also converge. And then similarly, if you draw okay, let me back up. These rectangles can be drawn this way, where they are underneath the curve, or they could be drawn this way, right, where they're actually above the curve. Do you agree that this could just be shifted? This whole thing could just be shifted over 1, okay? If you do that, the area of that first rectangle, which is the value of the series at 1, is 1.5 for this particular one. And then to that, you could add the integral from 1 to infinity, or the series, I guess, from n equals 1 to infinity, right? Because that would take care, here's the 1.5, right? That's the area of that rectangle. And then I could add to it all of these other rectangles, and it would still converge, okay? Because all you're doing is taking this area, which is underneath the curve, and adding an area of 1.5 to it. If the integral diverges, it's easy to see that if you draw your rectangles this way, that it would also diverge, right? Because if the area under the curve diverges and your rectangles are drawn above it, then that would also diverge. So that's why with the integral test, if the integral converges, the series converges. If it diverges, then it would also diverge. And there's more to it than this, and I have a really good animation that I hope to show you at the end of the period that will maybe help once again with this for those of you that are interested. I know I've lost half of you don't care about this topic anymore, but just in case you do, I've got one other thing that can help. But so the last thing that we learned yesterday was we talked about how if I estimate the sum of the series using a partial sum, right? I just add together, I think we did S sub 6. I add together the first 6 terms. That gives me an estimate of the sum of the series. And then whatever little rectangles remain underneath would be kind of the max error associated with my sum, right? The remaining area of rectangles would represent the y values that I could continue to add to my series if I kept going and did more terms of my partial sum. Okay, so that was that idea of the remainder yesterday. And then the last thing we talked about yesterday very hurriedly was the P series, right? And we said that if I'm looking at a power series, and by power series we mean where you have an exponent on the variable in your denominator. We talked about the pattern you see with the power, and we said that if the power is greater than 1, then the integral converges, therefore the series would converge. Okay? If the power is 1 or it's less than 1, then the integral would diverge, which means the series diverges. So that is its own other little test, the P series test. Okay? So we've got the integral test where we can actually find the integral, or we see this pattern that develops with anytime we do integrals on expressions such as these. And so if that power is greater than 1, then I can say that it automatically converges and I don't have to go through the process of evaluating the integral anymore. So that's where we are prior to the start of today's lesson. Victoria?
Should we write that down?
Did y'all not get to write this down at all yesterday? Okay. Okay. I think it's up to you whether or not you want to write them down. You've done these a number of times before, like this integrated to give you ln x, which was ln b minus ln 1. Okay. So you can write them down if you want, if you would feel better about doing that. All I did was summarize what we found there. Okay? Yes, Skylar.
So can I use that as justification for convergence and divergence?
Yes, that's what you will do. Okay, so when we talk about homework, which is what we're going to do next, you'll see that you can use that as a justification. If you are asked about the series from n equals 1 to infinity of 1 over 1 over n to the 4th, you just say convergent P series, since P is greater than 1. Okay, and that would be the sort of thing that you write in your homework. But I want to show you that so you know exactly what you need to show in your homework. Mary?
What does it mean that it's a harmonic series?
That's just the special name given to that particular series where the power is 1.
Okay.
Okay? Yes, Michael?
Were we going to do harmonic series? Like, is that a part of
No, it's just part of the P series. We're not going to really do anything else with it. Just know that, you don't have to know it by name or anything like that. Just if the power is 1, it does have a special name. It's the harmonic series, and we know that it diverges. Okay? All right, so on your homework, you had some that were strictly, the integral test and the P series test, but then on those last 10, 79 through 89, where you were asked to determine convergence or divergence, you're going to have a section of problems like that now at the end of every homework assignment, where you get to apply whatever test you want to that particular set of problems to determine if they converge or diverge. I would always start with the nth term test, okay? And then from there, go through, your checklist to determine whether or not they converge or diverge. Yes, ma'am?
You have to write what test we use, right?
Yes, I want you to right now. You'll have to for me and like a quiz and your test. Once you get on the AP test, you don't have to because most of those are presented in multiple choice format. I just want to make sure that we're thinking through it correctly.
Every
Okay.
time we do the integral test, do you want us to do the positive continuous decreasing? Check for that.
You know what? When you're doing those now, the way that when you come across those problems now and they're not separated into the integral test section of the book, yeah, you should get in the habit of that. Because it really should apply before you use it at all. Okay, so on the homework, how did that go for you? What's that?
I don't know how to do it for
83? Oh, 83 is just a geometric. Kevin, it's just 2/3, right? It's 2/3 raised to the n power. So that's a geometric series because you're just multiplying by 2/3 each time, right?
Okay.
So since r is 2/3 and that value is less than 1, I get to say it's a convergent geometric series. Just recalling some of the things we've talked about before on 87, that's one of those that if you will recognize that pattern, it sure will make your life easy so that you don't have to let y equal that side and then ln and all that. Remember, we talked about that the other day. When you get into when you see this, it's e. If there was a 2 above that, it's e squared, and 8, e to the 8. And this was the one that we'd had in the homework. It was a k, so it was e to the k. Yes, Michael?
On 89, when you
Yes?
get it, when you do the integral and you get the negative 1 over 2, that squared or u squared or whatever.
Yes?
How does that equal 0?
I did the u comes to, I can't read my own writing right here. What was u equal to? Oh, I put back in the ln, it looks like. And I went from 2
Okay.
to infinity.
Yeah, mine started at 1, I didn't realize.
Oh, okay, got it. Yep. Anybody else? Can I answer questions for you?
Can I see 81?
81, sure. Oh yeah, on 81, if you'll just take remember whenever you multiply like bases, you can add their exponents. So if I add these exponents together, that gives me into the 5/4. Since 5/4 is greater than 1, I'd have a convergent p-series. So on 87, I would have just said that this equals E, therefore diverges by nth term test. Anybody else?
Wait, what test was 87?
87, I just did the nth term test because I know from like that over there on the board, right? The limit as n goes to infinity for this thing is equal to e, right? And if I do the nth term test and I get a value other than 0, I know that it automatically diverges.
What would make that equal 0? Or it would always equal like e to something, right?
This will equal e. This, the limit as n goes to infinity, this thing is e.
Okay.
So then if you're thinking about it in terms of a series, it's like you would be adding e over and over and over again to the previous sum.
There would never like be that equation with like or something that would equal anything other than e to like some power.
Correct, and it's that number right there that determines the power. If that's a 2, it's e squared. If it's a 3, it's e cubed.
Okay.
Okay? All right.
On 89, why does it end up being 0? Because I don't have it equal
I let u be ln,
to.
and then my du was 1 over n, so that gave me this. And then I integrated it to give me u to the negative 2 over negative 2. But instead of changing my limits of integration, because it was ln, I just put it back in as ln. So this is negative 1 over 2 ln n squared. So it starts at 2 and it goes to infinity, right? So when I do, well, I guess it's really a b. So it's negative 1 over 2 ln b squared minus negative 1 over 2 ln 2 squared. And this, the limit as b goes toward infinity. Oh, I see what you're saying. So you're questioning my 0.
Yes.
Gotcha. Yeah, because that goes to 0, right? I might not have finished it.
And then that's like one.
And then this is just, this is a value, right? So yeah, it's not 0 then. Thank you for fixing that. It's whatever, it's this thing right here.
So then it would be divergence,
No, sir, because I performed the integral test.
right?
If the integral converges, then the series converges.
Okay,
Yeah.
this is helpful.
It's a lot to keep straight, and that's why I've said over and over again, you really have to think through what everything means. Because if you get caught up memorizing rules, it could go very badly for you very fast. Because it's like, you know, if the limit is n approaches infinity for a sequence equals a number, it converges. But if it's for a series, it doesn't converge. So you really, if you'll think about the meaning on each of them, hopefully it's going to help you get it.
Coach Sanders, can you go through the meaning behind why an integral converges again? Or like why it converges when it gets a whole number or a number?
If the integral converges, here's a graph of the series, these rectangles, okay? If the integral converges, that means that the area underneath the curve is some finite number.
Okay.
Then this would also have to be a finite number because it's smaller than the actual integral.
Okay.
Does that make sense?
Yes.
Okay. Yes. Yes. Okay, so we're going to move on to 9-4. You okay, Brianna? Okay, you sure?
Okay.
9-4 harder.
I don't think so. But I don't know. I mean,
The series.
I don't know. I don't know if you're going to like it or not. Okay.
Did that. Would be like a